of you have your instructor for the case for this. So the topic is Introduction to Mathematical Modeling. I welcome you to the podium.
इतना हाइट चाहिए देख लो ट्राइपॉड की तरह.
Okay, first of all, I'd like to thank the organizers, especially secondary students, for taking this initiative to start this science club. Many of the faculty members have been thinking about this idea that there should be a science club where students can discuss topics that are interesting to them, that they are not able to during lectures. So, while there will be several faculty members giving lectures here, I would like to also say that students should make this a platform for exchanging ideas themselves. So I certainly hope, expect, at least from my campus students, that some of them will be giving lectures later in the semester. I don't want this to be like a classroom lecture, but I'm just going to be using chalk and blackboard. So those of you who came here with the idea that you're going to be seeing fancy slides or pretty pictures, you will be disappointed. But I'd like to talk about mathematical modeling.
देखो कॉपी निकाल के ठीक है.
And also I'm happy to see so many of you have turned up for this lecture. Although I don't know if the first year students
लाइट
are
जलाना आगे
necessarily
पीछे
happy to be seeing me for the 5th time this week.
आगे की कुछ लाइट जला दो. आगे की लाइट वो उधर साइड वाली नहीं जलाना.
So before we get into the subject, let's look at a very classical example from Greek history. So Greek philosophers and mathematicians, and this dates back to 600 BC and up to 300 BC. As you know, many Greek philosophers believed at that time that the shape of the earth is spherical, not flat. Before the Greeks came, this was not really, there was no general agreement on this particular issue. But as Pythagoras and Thales believed that the shape of the earth is spherical, and later on Aristotle, he actually, so around 340 BC, and I'm just mentioning Aristotle, but there were other players involved, and so Aristotle gave some arguments as to why the earth must be spherical in shape. And then 100 years after, so around 240 BC, so I'm sure everybody remembers this date, or many of you do. Eratosthenes, he had major contributions in many different fields, including mathematics. So one of his discoveries was to find a way to write down a sequence of prime numbers. So what he did was he took these ideas that these Greek philosophers had, that the earth is spherical, and he set out to measure the circumference of the earth. And just imagine trying to do that more than 200 years, 2000 years. So what he did was, so he wanted to, he calculated the circumference of the earth. And the way he did that was he idealized assumptions. So first of all, his assumption was that Earth is perfectly spherical, right? Although now we know that that's not actually true. Earth is flat here, flatter near the poles. So it's like an orange which you just step on an orange gently and it just gets squished. And so, but at that, so his idea was that the Earth is perfectly spherical. So his assumptions, I'm just going to write them down. So here is a perfect sphere. And secondly, the light rays that come from the sun, they are parallel, right? Which in most, for all practical purposes, we consider that to be true. So using that, what he did was he looked at, so he also knew he resided in Alexandria. And what he did was I forget the name of the city. Something like this. So there was another city at which it was observed that at high noon, that means at 12 o'clock, the sun was exactly overhead. That means that the angle of elevation of the sun at that place, at that particular time, was 90 degrees. So he made that the reference, and he then calculated the angle of elevation of the sun in Alexandria. He found that there was a 7-degree difference. So moreover, he knew the distance between these two cities, which was actually calculated also in a very interesting way. Because in those days, there was no direct way of calculating distance between point A and point B. So what they did was they had to rely on indirect methods, like they would send a caravan of camels from one city to another, and then they would fix an average speed, and then the caravan would take several trips and they would just find the distance that way. So yeah, his idea was very simple, that this distance should be 7/360 of the total circumference. And his calculation turned out to be remarkably accurate. So basically, what exactly did he do? He took a problem in the quote-unquote real world, and he translated the problem into something mathematical, where he could apply the principles of geometry. Basically, that this angle he calculated using the properties of parallel lines. So his contribution was that he provided a mathematical context for studying a problem like this. So for using geometric techniques. So in general, this is what mathematical modeling is about. As scientists, one of the main goals is to understand nature as accurately as we can. So the objective is to understand nature, and perhaps if we have sufficient knowledge to solve problems that we encounter in the real world. Just explain what I mean by that. I'm going to give you a couple of interesting examples. So, basically, purpose is to understand nature and try to explain the so-called real world in mathematical terms. Right, so why would we want to do this? So one of the reasons is that when you when you look at the real world in mathematical terms, you can use the techniques and the theorems that are contained as well. So you can use the wealth of techniques to make logical deductions. And that is one of our aims, is to understand nature in a logical fashion. So, if you are looking at a physical system and you would like to write a corresponding mathematical model, where should we start? So obviously the first thing should be to define the problem in a way that can be answered mathematically, otherwise there will be no point. So the key elements of mathematical modeling are as follows. First of all, you have to formulate the problem. For example, you can think of if you want to study the evolution of the population of a certain species in a given environment. Right? That is, let's say that's our problem. So what we would like to do is, we would like to build a model that explains this particular situation. So developing the model, it means identifying the key variables. So identifying variables and parameters. Right, so obviously if you're going to study the evolution of population, then population at any given instant should be an important variable. Okay. So I'm going to consider these parameters when we look at the example. And then how are these parameters and variables related? The relationship, that's the important part. The relationship is really about right? Of course, if your problem is so complex that you are not able to identify all variables and parameters, you have to make some assumptions. Right? So, for example, if you're studying the motion and you are having difficulty, or you may want to, you may just want to assume that there's no friction or things like that. But just make an idealized model, and then relationship between the above allows you to write mathematical equations. So just writing equations is not enough, obviously. You would like to make sense of them first. If you get a set of equations that are internally inconsistent, meaning that one equation contradicts the other, then obviously there's something wrong with the model.